Welcome to a video on section 10.2 regarding arithmetic sequences. We'll also combine this video with section 10.3 regarding geometric sequences. So first off, what is an arithmetic sequence? As you see in the definition below, it's simply a sequence in which each term after the first term differs from the preceding term by a constant amount. Okay, that actually does seem a little confusing. So really what it is just a pattern of numbers with a common difference between consecutive terms. I'll give you an example. So a good example would be like this: 2, 5, 8, 11, 14, 17, and so forth. So notice how every number differs by 3, or I'm adding 3 over and over again. You can also subtract by the same number, but the bottom line is it's got to be consistent. So the difference between consecutive terms is what we call the common difference of the sequence. So if you look at example 1 here, you're asked to decide if it is an arithmetic sequence, and if so, what is the common difference? So we see -5, -2, 1, 4, 7. So we do see a difference of 3, so I'd say yes. And of course, we'll say the difference is 3. And just keep things simple, I'll use the variable d to represent the common difference. Now for b, looks like we're going down by 5 consistently, so I'd say yes again. My common difference is -5. Lastly, for c, we go up by 6 to go from 2 to 8, but then go from 8 to 12 to go up by 4, then back up by 6 and up by 4. It's not consistent. So I'd say no. There's a pattern for sure. But not a common difference. Now, there are some formulas associated with this. One form that we're going to use is called the recursive formula. It looks a little funky. If you kind of break down the words, you see the first 5 letters recur. Recur means repeat. And that's what we're doing here. We're trying to repeat things. Now, the subscripts are also a little confusing too. So you see A1. That just represents the first number in our sequence. So naturally, A2 would be the second number, A3 would be the third number, A4 would be the fourth number, and so forth. Now, this right here is actually the recursive formula. As you can see, what we're doing is we're taking the new term, which I'll call AN, equals the previous term, which I'll call AN minus 1, plus the common difference. So let me give you a good example down below. And actually, before I answer the question, because example 2 does ask us to say to write a recursive form for each arithmetic sequence above, let me actually work out the table below and then come back and do example 2. So here we have 5 n values. So obviously, if n is 1, then an is just a1, then a2, a3, a4, a5. That's how I label those terms. And of course, given the sequence above, so the way this is going to work, I know that a1 is 1, a2 is 4, a3 is 7, a4 is 10, and a5 is 13. Now, the way these work is you're doing an let me take this back a little bit. We'll put the common difference here, and I'll write this. So the common difference, as we see here, is 3. Every time, right? We add 3 to get from 1 to 4, add 3 again to 4 to 7, and so forth. Now, this is the recursive formula. And what you're doing is you're saying A2, actually I'll do it down here, A2 equals A1 plus 3, or A3 equals A2 plus 3, or A4 equals A3 plus 3, or A5 equals A4 plus 3. Hopefully you can see why we call this recurring. What you're doing is you're taking the previous term to get the new term. So again, we knew A1 was 1. So 1 plus 3, of course, is 4. And then 4 plus 3 is 7. And 7 plus 3 is 10. And 10 plus 3 is 13. So now, to write a recursive form for each of the sequence above. So when we had -5 as our first term, then what you would say is that an equals an minus 1 plus 3. And the reason why you write that is because when n equals 2, a2 would be a of 2 minus 1 plus 3, or a2 would be a1 plus 3. Now that would make sense because, of course, a1 is -5. If you add 3 to -5, you get -2. And then when n equals 3, a3 is a3 minus 1 plus 3, or a3 is just a2 plus 3. Well, what's a2? a2 is -2. -2 plus 3 is 1. And you kind of just keep going in that fashion. So actually, I just realized that I didn't use this table correctly. Sorry about that. That's okay, because I'll talk about the explicit formula down below. So the recursive form doesn't seem like a very efficient way. Like if I have to, like for example, for the one that I have highlighted in yellow here, -5, -2, 1, 4, 7. If I'm doing a recursive formula, and I want to find, say, like the 20th number in that sequence, I have to keep adding 3 several times until I get the 20th number. And again, that doesn't seem to be very efficient. I mean, I could do it and say, okay, -5, -2, 1, 4, 7, 10, 13, 16, 19, 22, 25, 28, 31. Okay, I already lost count. I don't know where I am right now. So you could do what I did here in red, just keep adding 3 over and over again. And the way it works is you just write an equals an minus 1 plus 3, and of course know that the first term is -5, so you kind of know how to get this thing started. But the explicit form is going to be a little bit more efficient. And let me show you how that works. It's going to be written like this. Now, a1 represents the first number. N is the number of terms we're looking at. Terms are just, numbers in the sequence. And D, of course, is the common difference. So here you're asked to find the 10th term. So that means n is 10. I want a10. I want the 10th term. Well, the first term I know is 1. I want 10 terms. I'm doing 10 minus 1. And the common difference, if you just look at it, you're adding 3 over and over again. So you do that. So it's 1 plus 9 times 3, 1 plus 27, 28. So if you were to use your fingers, 1, 4, 7, 10, 13, okay, that's 5 terms, 16, 19, 22, 25, 28. Hopefully by the time you've counted up to 10 terms, you stumble upon 28. Again, doing it recursively, I don't know if it's necessarily a great technique. It's good to talk about recursive sequences because those are things that can show up in later math courses. They can show up on the ACT or SAT. But in terms of being efficient for this unit, we're going to use explicit. And if you think about what the word explicit means, if you think about like maybe watching a movie with very explicit lines, or listen to a song with explicit lyrics, they're being very direct, using most likely profanity. And of course, when you do use profanity, you are being very direct. So explicit kind of means the same thing. Okay, so here's the formula, as I just shared with you guys. So we'll do some examples here, and then I'll probably let you guys do the second sheet that says 10-point arithmetic sequence part 2 on your own, so you can practice those skills. Okay, so let's look at number 1 here. Find the 8th term of the arithmetic sequence. Its first term is 4, common difference is -7. Okay, well that's easy. You want A8. Now your first term is 4. You have 8 terms times -7. Need a calculator? Go ahead. Actually, probably a good idea to use a calculator so you don't make mistakes. But I think I did this right. So -45. And that would make sense because we're going down by 7 every time, starting with 4. Now, for number 2, if you have to write an explicit formula, well, that shouldn't be too bad. An equals your first term plus n minus 1 times 6. Now, we don't know what term we want, but this will enable us to find any term within that sequence. Well, here's another one. Actually, I'll let you guys do this on your own. So it's the same thing as number 2, so I won't do this one. I'll let you guys do it. Okay, big concept number 3. Find the contrast between two terms. Okay, well, that's obvious. You have the 5th term, you have the 6th term, your difference is 5. But then notice how we have the 4th term and the 6th term, the 1st term, the 4th term, 3rd term, 7th term. Those are not as easy to figure out. What you could do is simply just do this. 14 minus 6 over 6 minus 4. Where am I getting that from? Well, 14 minus 6 are given to me two terms, which of course is 8. Why the 6 minus 4? Because I'm given the 6th term and the 4th term. So obviously that's a jump of 2 terms to go from the 4th term to the 6th term. So of course I get 4 here, and that's my common difference. That's my d value. So if you think about it, if your 4th term is 6, if you add 4 to it, you get 10. That's your 5th term. Add 4 again, you get 14. Now that's your 6th term. So you're using a little bit of logic here. Basically what you're asking yourself is, how many times must I apply common difference to get from one term to the next? How many times must I apply the common difference to get from one term to the next? So let's look at C. You have the 1st term, you have the 4th term. So you can use your fingers if you need to. How many times must I go from the 1st term? How many times must I add the common difference to get from the 1st term to the 4th term? Well, I have to add it once to get to the 2nd term. I have to add it again to get to the 3rd term. I have to add it again to get to the 4th term. You've applied the common difference 3 times. Or just do 11 minus 2 over 4 minus 1. 9 over 3, 3. Lastly, for this one here, you're doing 9 minus 3 over 7 minus 3. 6/4 or 1.5. Here it says, can you come up with a formula to find the common difference given any two terms? Well, yeah, I just did it for you. It's m minus n over little m minus little n. So capital M minus capital N over little m minus little n. So on this next page, 10.2 sequence, it's handwritten as part 2. I'm going to let you guys work through these. I'm not going to do these for you. This is a great chance for you to do a little group work after the video is over. But let me talk about example 3, because that one's a little funky. Now, the one thing that you may want to do is you may want to grab a yellow graphing calculator. or if you have your own graph calculator, you can use that. So what you need to do here is hit the alpha button and hit window. You will see that symbol appear. And this is called sigma, if you're curious. And it stands for summation, meaning you're adding a bunch of terms. And what are we adding? Well, we're adding things based upon the formula that's given to us. I is our formula. It's a very simple formula because apparently you're told that I equals 1, and then you see 100 up top. The I equals 1 is where you start. 100 up top is where you end. And you go up in increments of 1. So hopefully that might seem logical. So, for example, if I plug 1 into I get 1. If I plug 2 into I get 2. Plug in 3 into I get 3. Plug in 4 into I get 4. Until you plug in the last number, you get 100. So what this is asking you to do is add up from 1 to 100. Now you could do that manually, which would be insane. What I recommend that you do is use a calculator. There's that feature says alpha window. It's going to look kind of like this. So you may want to have a calculator out, pause the video and grab one. You're going to see kind of like a little box equaling some box, another box here, another box there. That's kind of how it looks. What you can do is put an X in the box. You can use X is like near the top of the calculator. Then of course put the 1, put the 100s, and then put X right there. And you just let the calculator do its magic. It will actually work out for you. But there is a formula that goes with it. And the formula is down below. And so AI, again, is your formula. I equals 1 is where you start. And N, of course, where you end. And because it's an arithmetic series, apparently the formula will look like this. And so N being the number of terms, A1 being the first term, N being the last term, and of course just divide by 2. So if I were to apply step 1 to this, and remember this is an arithmetic sequence because we are going up by 1 consistently. Column difference is 1, right? But all I need to do is take the number of terms, which is 100, 1 plus 100 divided by 2, and I think you would get 55, 50. This is where, and you should use a calculator. Sorry, 50-50. So this could be a very handy formula to use instead of just adding up this number over and over again. Now, of course, I gave you the formula to use. What if I didn't give that formula? Sometimes it's a little tougher to work out. And we're going to see that in example 5. So let me do example 4 part A, example 5 part A, and of course we'll have you do the part B's on your own. So for example 4, you're asked to work that. You could just use your calculator now that you know the feature. Remember alpha window. But what if I didn't give you a calculator? What you would recognize that the formula is 2i minus 1. Your first term is 1. Your second term, I think, is 3. Your third term is 5. Ooh, we're going up by 2 over and over again. Okay, we're going up by 2 over and over again. The last term, of course, is 39. Interesting. So I have 20 terms. 1 plus 39 divided by 2. Work it out. You have 10 times 20, and you get 200. So yeah, pretty simple. But you can use a calculator also. But this did follow a arithmetic sequence pattern. Let's say we try to find this out. So we see that the common difference is 3. We see that the first term is 2. And we see the last term is 59. Now, how many terms do we have? That might be a little tricky. So, how many terms do we have? Well, you can kind of go back and look at example 1, which is all the way back here. We see the form of an equals a1 plus n minus 1 times t. So, an equals a1 plus n minus 1 times t. So 59 is this, that's 2, that's 3. And so why am I doing this? Because it's a little hard for me to tell how many terms that we have. So if I were to work this out, I get 57 equals 3n minus 3. 60 equals 3n, so it looks like I have 20 terms. And actually, I could have used a bit of logic also if I so desire. I could have done 59 minus 2. And I know the common difference is 3. That 57 or question mark equals 3. So if I solve for the question mark here, you would get 19. So it means that after the first term, I have to add the common difference 19 times. Well, 1 plus 19 is 20. So you could also think of it that way as well. But I know some of you are a little more formula driven. And so if you do use the formula to find a particular term, the explicit formula, you could just use this right here. So let's move on to a geometric sequence. Okay, I'm back. Sorry for the slight commotion there. I had my son running around the house. Geometric sequence, okay. So that's when you're multiplying the same term over and over again. So it's very similar to an arithmetic sequence. It has a consistency, but now we're looking at a common ratio. So for example, 5, 25, 125, 625 looks like we're multiplying by 5 over again. So I'd say yes. And we're going to use little r. You're multiplying by 5. But here I'd say no. In this case, it's a arithmetic sequence. You're adding by 3 over and over. It's not a geometric sequence. So a geometric sequence is you multiply by the same number over and over again to get each new term. Here I'd say yes again. And our common ratio is going to be -2. Now there is a recursive formula that goes with it. And in this case, you're doing an equals an minus 1 times r. So what you're doing, say for part A here, is you're going to say the first term is 5. And then an is your new term. An minus 1 is your previous term. And multiply by 5. So this way, when you try to find a2, you do a1 times 5, you get 25. If you do a3, you just do that. And then for this one here, you say the first term is -12. And then an is an minus 1 times 5. Sorry, times -2. Because you're multiplying by -2 over again for c. So again, this is the new term. That's the previous term. Okay. So explicit form of geometric sequence. Now, the way this would work, now I'm going to fill out this table correctly because I didn't do that last time correctly. It's simply just going to be, we're going to put r right here. So of course our first term is 2, our second term is 4, 8, 16, 32. And we're multiplying by r, so it looks like our r in this case is 2. And of course, this gets us the next term, which of course is 4, 8, 16, 32, and 64. That'll be the next term. So if you think about it, you're multiplying r over and over and over again. So there is actually a formula that goes with it, which is right here. That's on the next page. So you basically take a1 and multiply by r a certain number of times until you get to what you desire. So if I wanted the 10th term, sure, I could multiply by 2 multiple times, or I could just say a10 equals 2 times my common ratio, which is 2, raised to the 10 minus 1 power. What this tells us is you're multiplying by 2 9 times, because you want to get from the first term to the 10th term. So that means, if you have 2 as your first term, 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, 10, 24, you could use your fingers and do the mental math. Or you could just use a calculator and make it pretty easy for yourself. That's 2 times 2 to the 9th power, 2 times 2 to the 9th is 512. So of course you get 10.4. Right. So let's do maybe some examples here. Then we'll end this video because it is getting pretty long. Find the eighth term of geometric sequence whose first term is -4, common ratio is -2. So, okay, I want the eighth term. -4 is the first term, times -2 raised to the 8 minus 1 power. Remember, n is 8. A1 is -4. Your r is -2. And then you can just let the calculator do its thing. Remember, you got to put the -2 in parentheses, so you follow the order of operations. So you should get 512 for that one, if you do it all correct in the calculator. For example 2 here, if you're asked to write the explicit formula, well, I'm going to say an equals my first term, which is 3, times my common ratio. Hopefully you can see the common ratio is 2. You multiply by 2. That's just more by inspection. Raised to n minus 1. And as a habit, I always like to surround r in parentheses. So I'll let you try example 3 on your own. And then lastly, we have something called a geometric series. So a series is when you're adding up all the terms. So I didn't really make that distinction very clear. It equals just a list of numbers. The series is a sum of numbers. So when we did the sigma notation thing earlier on for the arithmetic pattern, that was actually called an arithmetic series, not a sequence. So that's a series right there. Sequence is more just a pattern. Not sure if it makes any sense, but if you think about like in baseball, the World Series, usually the World Series is the best of 7 games, or in the playoffs, now we have the Western Conference Series between the Houston Rockets and Golden State Warriors. It's kind of the sum of all those games, right? Would be the series, I guess. If that makes any sense. But of course, there's a pattern. The games, kind of make up a sequence. I don't know if that makes any sense. So I tried. But there is a formula that goes. I'm not going to actually derive it. I'm just going to kind of give you the formula straight up. So we'll just kind of forget about the derivation. That just is kind of crazy. It looks like this. It's a1 has 1 minus r to the n power over 1 minus r. This enables you to find the sum of all the terms in a geometric sequence. So we call that the sum of the geometric. This actually should be a geometric series, by the way. So make sure we get the terms right. So S just represents the sum, N is like the number of terms you're adding up. Just like we saw kind of over here, but we should have used the letter SN for that. That's another way we sometimes express that. So anyway, you can use a calculator again. Now you know where this is located. Remember alpha window. But what you could do is if you start by putting I equals 1 into the formula, you'd have this. Which of course is 2 times n to the 0 power is 1, so 2 is your first term. So all you really need to do is know what your first term is. And hopefully you can see that the ratio is negative 1/4, because if you were to do I equals 2, here's what's going to happen. Now you get negative 1/2. So it looks like you're multiplying by negative 1/4 over and over again. And that has to be risen to the n power. And you remember, you want to put the r in parentheses just to be safe. We are doing 10 terms. It's going from I equals 1 to I equals 10. 10 is definitely going to be 10. Over 1 minus negative 1/4. And then you let the calculator work its magic. I'm actually going to use a sigma notation formula in the calculator under alpha window. But x equals 1, 10, the formula is 2 times, and then parentheses, I'll do negative 0.25 raised to the x minus 1 power. And the calculator does its magic for you. You should get about 1.6 for that one. We see another one with number 2, so you can try that on your own. You could just use a calculator, but if I did ask you to show the work, what you'd want to do is first calculate the first term, which you're going to find is 16, and then find the common ratio, which you're going to find is 1/2, and then you plug it all into the formula you see here. Now, sometimes you'll see something called an infinite series. It's one that goes on forever. So, you have like A1 plus A2 plus ... So that just means it's infinite, it's going on forever. But this is a series that follows in geometric pattern. So let me give you a good example. Let's say I have like 8, 4, 2, 1, 1/2, 1/4, 1/8. Hope you see the pattern that I'm actually multiplying by 1/2 over and over again. So if your r value is less than 1, and I put absolute value of r because your ratio could also be negative, but you don't want to be too negative. So if it's contained between -1 and 1, not inclusive, then there's actually a way you could find the sum of the infinite series. So even though there are an infinite number of terms, so you don't know what n is infinity, but you can still find the sum, and the sum will just be this. I'll use the infinity symbol as a subscript. It's actually pretty simple formula. It's just that. And that's what we could discuss in class why that is. But if you think about it, if you have a very small value for r and you're raising it to a big exponent, it's pretty much just going to vanish. And that's why you have just a1 up top. So that's the real reason why. Again, if you take like 1/2 and raise it to like the 10 power, it becomes super, super tiny. The r to the n in the numerator just kind of goes away. So you're stuck with a1 over 1 minus r. So I'll do this for maybe just example 3, and I'll let you guys try example 4 on your own. In this case, we're actually starting with a different number, n equals 0 instead of n equals 1, and we're using a different letter n, doesn't really matter. So my first term, n equals 0, is 0.4 to the 0 power, which of course straight up is 1. If I'm curious what my second term is, so I put in the next one, n equals 1, I get 0.4 to n equals 2. So it looks like we're multiplying by 0.4 over and over again. So I can just use this formula, because my r value is definitely between -1 and 1. So a1 1 minus r, 1 over 1 minus 0.4, 1 over 0.6, which would be about 1.667. Or if you were to convert that to a fraction, it would be 5/3. So even though n is infinity, what's going to happen is that ultimately the later terms become so tiny that it's almost negligible in the overall sum. So it doesn't really matter. So I know this is a lot of material, and of course it's brand new for many of you. So if you're a little confused or thoroughly confused, and I'm sure you guys are laughing, that's okay. But you've seen it once, and as usual with most things, you guys see it multiple times. Math sometimes doesn't come easily the first time around. That's actually true for everyone. Those who've done a lot of math in their life, like me, um, calculus was hard the first time, and some of the stuff also was hard too. And so sometimes you have to kind of look at it again, have some guidance, which of course I'm always there to help you guys out. So yeah, so try the rest of the problems, work with each other. Um, we'll definitely do a little more work on this, and we'll do a project on this stuff um, later in the week. So okay, that concludes the video.